A very good afternoon to all of you. Today's presentation would be about GIS data model, raster and vector, their inputting and editing. So I would just start. Spatial data model. It's actually like where we talked about it yesterday too, like about data, what are data and what are their utility in bringing out in spatial data. For example, this data gives us information about the spatial location or whatever. So data are the observation made from real world experiences, organized and processed in order to make them meaningful and convert them into information. So the basic is to retrieve information, and data may have three modes or dimensions. So they are spatial, thematic, and temporal. So spatially, it talks about the location, like where it is geographically located. It talks about its extension or its position in the space. Thematic means what its attributes, and temporal, how data. It's basically the type of data. Like every data has these attributes, these three characteristics attached with it. So the real world is too complex for immediate and direct understanding. So we create models or abstractions using data that are intended to have some similarity with selected aspects of the real world. So what do we do in the GIS basically when we talk about? So we try to create models of the real. We try to abstract the reality into some form which is much more convenient to use upon, to work upon. So these are models, and in geography to represent spatiality of like geographical locations and geographical positions, we draw some models, which some abstraction in some forms, which makes it more convenient to present whatever queries whatever we are concerned with. So representing geographical features, how do we describe geographical features? So by recognizing two types of data. There are basically two types of data which we discussed in the previous lecture too. Spatial data which describes the location. So where about the things, where do they locate, where geographically they are. So where about the things, it is dealt in the spatial data. And attribute data which specifies characteristics at that location, the how much, what, and when. So basically in this lecture we would be discussing about the spatial data, and of course in GIS these two kind of data are really important, like where of things and how much of things. So we work upon in spatial data. For example, we tend to look at the location of things, how it is distributed, and in attribute data we see that how, for example, the location of what kind of vegetation, what kind of soil, this all are dealt in with the attribute. It is the attribute data which gives characteristics of the specific locations or the regions or the area wherever we are concerned with. So how do we represent this digitally in the GIS? So how do we represent these geographical data in the GIS? So by grouping, it basically groups, like it's a model of storing the information of the real world. It does it basically into layers with every character, every geographical characteristics. They have their own layer, like hydrography, elevation, and basically we divide the real world into various layers of information, and it is stored in various layers of information. So that basically gives us one benefit of dealing with each characteristics of real world separately. So basically we have two kind of models in which we represent the real world digitally in the GIS. So these are vector data model first, and the second is raster data model. So by selecting appropriate data properties for each layer with respect to what the projection is like projection. We just sir just discussed about that, how we represent this, try to represent this surface on a plane, earth on a spherical earth on a plane surface. And about the scale, the scale is basically what area is being, what area, how much of it, actually a unit of area is being represented on a map in a much smaller unit. So accuracy is about like we try to present the reality on much more on a model in much more small, in a much more in such a manner to deal with it, to see things more precisely. So accuracy is the extent to make it as near to the reality as we could. And another thing, when we talk about the spatial data, and particularly about images, the representation of the earth, so we talk about the resolution. So resolution, for example, on a map or on an image particularly, it's about how precise these, it's a quality of how do we distinguish between two things of two things, like two things with or either it would be in their color or shape, whatever is the ability to distinguish between things. So it's all about distinguish between things. Firstly, it's a fundamental of how we distinguish the whatever the spatially whatever things or whatever. For example, we talk in an urban area, we when we talk about the different location or the pattern of network or whatever, when we talk about the economic activities carrying out in region, so we are basically dealing with dealing on differentiating or locating things. The concept of vector and data, vector and raster. So basically we try to represent the world into two forms. In raster, it's basically in raster representation, what we try to do, we try to divide the world into grids, small grids or cells or whatever. We try to perceive the real world into a grid form. So each of these a pursuit of this grid, which are arranged as in rows and columns, they retrieve the real earth information in the form in a cell, which is a representation of that part or of the real earth on the real surface. So every attribute, a data about a value about every location on the earth of the similar grid, it's been retrieved, and that gives us the information about it. So raster representation is about taking the information and arranging it into a grid form, while vector representation it's basically utilizes the fact or the principle that every object on the surface of the earth, they have a certain kind of shape. They can be represented in a unique form of polygon or a line area or a point. So starting with raster data model, the raster data model fundamentally is based upon the principle that real earth surface can be divided into regular grid systems, which are called pixels or cells, to cover the space and the value in each to correspond to characteristics of a spatial phenomena on the cell location. So like we discussed, so it tries to divide the real earth into certain grids, and each grid would retrieve data about the location which it represents on the surface. So through it, we try to collect the data about the real earth. So conceptually, the variation of spatial phenomena is reflected by the change in the cell value. So variation on the real ground or real surface is actually reflected by the change in the cell value. So there is a change. For example, in this we have different value. For example, R is one value, and T is one value, and H is one value. So we distinguish between things on whatever on the real earth. We perceive the changes on real earth by by the changing amount of the data, the value of the data in the grids. So so the area is covered by grid of a grid of equal size cells. So every grid would be of equal size, and location of each cell calculated from the origin of the grid. And location of each cells in a grid, when we talk about the location of a grid, it's calculated from the top left corner of the image, or whatever data we are in the form, if it's in the form of an image or in other form. So we calculate it from the top left corner, and cells often called pixels. The raster data model called image data. So cells are called pixels too, which is the picture element which carries the attribute data, which the value actually represents the attribute data. And raster data often called an image data, and it's also called image data because every kind of image we have, even when we take pictures in our cell phones, it's actually in a form of raster data. So each pixel have a single value. Each pixel is a unique, has a single value, and it's unique in a sense that it represents, it's unique to every kind of attribute, every kind of attribute. Like the road, when we talk about road, it will have a unique value, and as we compare with another attribute. So attributes are recorded by assigning each cell a single value based on majority feature in the cell, such as line type use. So this raster model, when we talk about, it's very easy for us to analyze or overlays, to do analysis and overlays just by combining or what do they do? They're just by addition of data for some addition of values or subtraction of values. They gives us analysis. For example, when we talk about yield, which is of course would be an addition of rainfall and whatever, how much rainfall is there, and what amount of fertilizer we use. So raster data calculates it, combines it. Helps us to combine and analyze data, and which is why in a real faster manner, which is why raster are often called the faster one when we talk about bringing things into practice. It's relative to the vector model, it's much faster. So simple data structure and directly stored, each layer is a single table. So in the raster model, so we store each layers as a single table, like each layer has a single kind of information, and computer database management system is not required. Yeah, this is one of the important characteristic of this raster model. A raster model in itself is a kind of database management, so it's not required. While for the vector model, we need a system to record. For example, when we see an image, it itself is in the form of raster model, so it in itself is complete. So it doesn't need any system to be analyzed upon. While the raster model, when you talk about the vector model, to work upon it, to manipulate, we need to do it in a database management system. So data model, a raster data model uses a grid. So grid are actually the building blocks of this raster data. So one grid cell is a unit or holds an attribute. Every cell has a value. Every cell has a value, even if it's missing. So in this kind of, when you talk about these cells or pixels, even 0 is considered to be a value. Like it's known data, but it's still a value. It represents that it represents the absence of the data. Like it gives a sign of some attribute. So a cell can hold a number or index value standing for an attribute. So a cell basically holds a number, which like a particular number, which gives us information about the attribute. So a cell has a resolution. So resolution, when we talk about this raster model, it's an important concept, and given as a cell in the ground unit. So resolution actually it's when we talk about this raster data, it depends directly upon the size of the cells actually. Well, what's the cells and the ratio, like the ratio of the size of the cell and what proportion of the earth, the real earth, it represents. So smaller the grid system, smaller the cell size, and greater would be the resolution. So resolution, it directly depends upon the cell size of the cell. The size of the cell in a raster model is an important factor. Small cells improve image quality because they increase details. So smaller the cell, small will be the detail. Like smaller will be cell, smaller area would it be engulfing in itself. So the data would be of much smaller area. So it gives us more detail. So small cells improve image quality because they increase detail. As cell size increases, image definition decreases or blurs. As the cell size increases, it gives us very vague information about the reality. Cell or pixel size in a raster file is referred to it as resolution. The spatial resolution is defined as the size of smallest recording unit or the smallest size of geographic area represented by a pixel. So for a scanned image, we often use the term DPI, like DPI or PPI dots per inch or PPI. So it gives us information about the quality of information about the reality we have. It gives like when we have a more number of dots or pixels per unit area, it gives us more information about the area, more detailed information. For example, like an image, for an image, or when we say it's a 300 DPI, it actually describes that 1 square inch of image contains 300 columns and 300 rows. So the total would be a multiply of these two. So higher resolution which always give more clarity. So higher the resolution and higher would be the clarity of information. So this is basically what we do in a raster model. We divide the real world into grids and then try to perceive each grid with say, for example, when we divide in the second image, when we apply the grid upon the earth, we can see that each grid have different attributes, like different attributes. Sometimes it happens sometimes, and so there is also a way in which an average or there are rules, for example, what is the centrally located or which attributes cover maximum data. So there would always be a single value. There can't be two values for a grid. So and in the third image where the grid is finer, it gives us more detail about the reality. For example, in the coarser one, we have we have a single cell engulfing different features. So it gives us very blurred information about the reality. So boundary problem handled by mixed bags, we talk about that each grid, sometimes grids tend to cover more than one information of or more than one attribute on the ground. So there to solve this, we have the largest share. So whatever the in figure 1a, which it regularize the value, or it singularize the value using the largest share. Like in the grid second, we have the largest share of the pink area. So it regularizes it. But in this there is one more thing one more way in which we could calculate it, or we could singularize the data, is the central point rule. So whatever is located in the center of what data or attribute covers the central point, it would be regularized it would be generalized for the whole grid or pixel. So data, basically, when we talk about it's a when we zoom is the basic it's this slide, this project, this image actually to bring out how in the images of our daily use, how these are arranged in. For example, see, when we zoom it and further zoom it, how different values, how it's sometimes difficult for us to imagine that how values of like grids of different values could actually result in the creation of a real image. So here it is, like when we zoom, when we further go deeper into the image, so each value, each grid has a singular value. So with a combination of various values, like values of multitude, like millions of this forms of values, we try to represent the reality. So there are classification of raster images, raster data. Like the raster can be classified according to the color concept and source. So first, the color concept. Like according to color concept, raster data can be classified as binary image, grayscale image, and color images. So first, the binary images. So actually, it's on how we retrieve the data in. Like in a binary image, we only retrieve the value in either one or zero, either yes or either. And there's in binary itself, it means putting in the information on in just two values, 1 or 0. So only discrete geographical objects can be represented by binary image. So only discrete in geographical, like which has much variation can be represented in a binary image, because it only utilizes two values. For example, for example, when we study about the flow of a river, like the direction and of a river, it could be done in this binary images too, because it gives, it contrasts, it compares it with the land surface. So we can't explain continuous data by the binary image, because it uses only two data to study about the reality. So each pixel of binary image uses 1 bit of information. And the second is grayscale image. An image represented with continuous tone as uniform shades of gray. So we use much more a wider range of data in this kind of images. For example, a pixel of grayscale image usually use 8 bits of information. So we have values from 0 to 255. So we can bring much more attribute. We can study much more attributes in this kind of images. Though the higher range of shades are also available in some remote sensing images. Though we have more than 8 bits, like 16-bit or 24 bits information, which use much more range of information to study about the attributes. So so human eyes commonly we can only differentiate approximately 40 to 50 individual shades of gray in a grayscale image. And the third one is color image. A color image is a digital image that includes color information for each pixel. So we have color besides we have the grayscale. We try to color the things to make things more distinguishable. We try to use the color band. So for visually acceptable result, it is necessary to provide 3 sample color bands for each pixel. We are interpreted as coordinates in some color space. So basically the 3 basic colors, the red, green, blue color space is commonly used in computer displays. So a color image is usually stored in memory as 3 separate raster maps, 1 for each band. So a color image actually is stored in always in a 3-layer, 3 separate raster map. So each of the layer would be representing one basic color. So on the base of source, raster data may also be classified. On the base of source, where do we get the data from? The raster data is classified as digital satellite image, where we acquire the data from through satellite sensor, digital aerial image, where we acquire the data with the help of aerial cameras, and scanned image. So a lot of data raster data we acquired through scanning. So it's acquired by optical scanner from an analog map or hard copy aerial photograph when we scan them. So when we get the data in that way, it's called scanned image. So second would be the vector data model, and it basically the basic vector data model is that is the assumption that the real world can be divided into clearly defined elements, each of which consists of an identifiable object with its own geometry of points, line, or area. So object-based models treat geographic space as a space populated by discrete and identifiable objects. Example, buildings, highways. So it basically, as I talked about earlier, it basically uses the principle that how that each geographical space can be have their own discrete like identifiable. They can be they have their own linear or polygonous shapes. So we utilize it basically to distinguish between, for example, how the buildings have a definite kind of shapes, how like a polygonous shape, or so we utilize that principle to to bring out the reality. So representing data using a vector model. So we tend to divide, we classify things as in points. We represent the reality into points and a line and polygon. So point is actually a zero-dimensional single coordinate xy coordinate pair, and it doesn't have any area, and it usually is represents the features like tree, oil well, or level location we have. And the line, when we represent the reality into line data, it has a single dimension and it has two or more connected coordinates. So we use line or arc data to represent roads or streams. And thirdly, we have polygons, and polygons in four or more orders and connected xy coordinates. So first and the last xy pair are the same. So actually, where it means that where a polygon, where it starts from, it ends over there. So that does result into the formation of the polygon. For example, in the third figure, like polygon 1, when one coordinate has been represented, when it starts from a coordinate 7, 2, it would end at the same coordinates, thus resulting into formation of a polygon. So the vector data model, a vector data model uses points stored by the real coordinates, and so requires a precise coordinate system. So we use geographic coordinate system, which is already there, latitude and longitude sometimes, and there's another form which is called Cartesian coordinate system, in which we use different reference points. And for example, when we usually locate something on the with reference to the xy coordinate system, we can do it. We can locate it in this way. And UTM, like in the previous presentation, Sir discussed how we divide the Earth into other in some other in more convenient way, so that we can study the Earth's surface. And UTM is one of it. And lines and areas are built from sequence of point in order. And lines have direction to the ordering of the point. Polygons can be built from points or lines. So vector data can store information about topology. So basically, a vector data, this is a vector data. So it basically uses points or lines and to represent the reality. So topology is one of the most important aspect of this when we study about the raster data. It actually creates the relation between the various points or polygons, whatever we represent the reality in. So it try to create a mathematical relationship. So it can be defined as a set of objects and data that defines the relationship between objects. So it try to create a relationship between the various objects when we locate various objects on the surface, on the map, or in the data. So topology, as it relates to spatial data, consists of three elements. Basically, topology consists of three kind of relationship. One is the adjacency, which defines the relationship of area sharing a common boundary. So it gives a relationship between two things which shares a common boundary. It defines where it locates either to the right side or the left side of it. So these relations, when we yeah, utilizes the the vector data later on in when in applications, it gives us really, for example, when we when we talk about the nearest distance or distances, it automatically provides us the information. And containment is one another relationship it creates, how which describes area features which may be wholly contained within another area form, such as for example an island within a lake. So it gives the relationship of containment, how one thing is contained within another thing. So, and the third is connectivity. So geographic property uses to describe the linkage between linear features. So it gives the connectivity, gives us linkages or the relationship between the linear features. So node, arc, and polygon, they are the basic, as we had the cell or the pixel in the raster form. Here in the vector form, we represent the reality. These are the basics to represent to the reality in the data. So there are so in topology, it tries to the topology. Basically, it tries to create relationship between like arc and node topology. Like arc and the nodes, it try to create relationship which define relationship between points by specifying which are connected from to what or from what arcs. It defines relationship between arcs by specifying which arcs are connected to form routes and networks. So the secondly, it gives relationship between polygon and the arc. So defines polygons by specifying which arc comprises their boundary, what arcs create the boundary with. So and left-right topology, where when we talk about adjacency, when we discussed, and it defines relationship between the polygons and defines from nodes to nodes, which permits left polygon or the right polygon to be specified, and also left side or the right side are characteristics. So why topology matters? So why topology is important? Topology actually allows automated error detection and elimination. Yeah, topology also, when we create relationship between the arcs and the polygons and the points, it tend to detect and eliminate the errors automatically. Rarely are maps topologically clean when digitized. When we acquire the vector data, we acquired it through digitization process, and it is full of like errors. So the topology helps in cleaning up like in automatic detection or elimination of these errors. A GIS has to be able to build topology from unconnected arcs and nodes that are close together. Like what the topology does, it closes or it snaps the nodes which are snapped, or wherever there is a gap or an error is there, it closes them together. And silvers are basically what when we digitize or when we create boundaries, there are small areas, like when there is an overlapping of two lines, there is small area remained over there. So when we do double digitization, so it is also being automatically eliminated by the topology. So here we are over with the raster and the vector model. Now we will talk about a bit about their advantages and disadvantages. First, raster model. It's simple data structure. Raster model is very simply defined and easy and efficient overlaying, which I discussed, that how the different sets of images can overlay and could be analyzed in a much more easier way. And they are compatible with remote sensing imagery. High spatial variability is efficiently represented through the raster model, and efficient to represent continuous data. The continuous data can much more be, for example, continuous data like temperature or elevation. When we talk about it can be much more better represented through the raster model. And it has some disadvantages too. Like data model, as we acquire data for each and every pixel, so the size of the file becomes very large. So it has a larger file size, All the objects are series of pixels, no identity for discrete objects other than points, like difficult to build topological relationships, insufficient projection transformation, loss of information when using large cells, and difficult to edit. They are relatively difficult to edit than the vector one. So talking about the vector model, the advantages: smaller file size. So we only draw the data about certain features which we are interested in. We don't do it for all of it. So the data size, file size actually tend to remain small, and the individual identity for discrete object like line, polygon. So they have an individual identity or individual layer for each discrete objects. So we can work on each objects or separately. And efficient for topological relationship. Yeah, we have topological relationship in vector model. And efficient projection transformation, accurate map output, and easy to edit. So it also has some disadvantages. The complex data structure. The data structure becomes very complex when we come at the end. When we comes with the data, it becomes very complex. So difficult overlay operation. So it's more as compared to it's very difficult to overlay vector model. So high spatial variability is inefficiently represented, not compatible with remote sensing imagery, not appropriate to represent continuous data. It basically represents mostly the discrete data and can't appropriately represent the continuous data. So here we can see in how the real world is represented differently in raster representation. Like in raster representation, how like an electric tower is represented as a point in a point in the vector representation, and it would use in the raster representation, it would use a cell or a grid. And how electric power lines, how the lines is drawn in using various grids in the raster operation, and how in vector it's only the point and line data. And the pond, for example, which is two-dimensional, and how it occupies various cells in the while we grids while we do it in the raster representation, and how a polygon is used while we doing it in the vector data model. So likewise the road networks and elevation also. And when we compare the raster and vector, it says the raster is faster but vector is correcter. So raster data model, a location is referred by grid cell in a rectangular array, while in a vector model location referred in x and y coordinates. So attribute is represented as a single value that is for the cell, while in a vector model the attributes refer to unique ID numbers to the table. Like much data comes in the form raster data comes from images from remote sensing sensors, right, and scan map and elevation data by USGS, United States Geological Survey. It is actually provided in the raster data form. But vector data form, it's actually rarely available. Like digital line graph by the USGS for streams is actually available in a vector data form. So let's continue what it can represent best. So the raster data model, it can represent elevation, temperature, soil type, land use, which are continuous in nature. It can represent it in a much better way. So likewise the vector data model, it represents property lines, political boundaries, and transportation much better. So this is an example. This is an overlay of an aerial photograph, which is raster with the vector data overlay. Like the line, the blue line and the yellow line, which they actually represent the vector data. So coming to the second section of our study, it's a data input and editing. So starting with data input, it's about how we put the data into a database to work upon, how we pursue the data from the real world, and how we put it into the database model,
What in?
the digital database. It involves some process. It involves, of course, some process that's solely dependent on the types of data. So the kind of processes we use, it depends upon the if the data, if the data is basically available in analog form, like paper form or hard copy form,
ಇನ್ನೊಂದು ಸೆಂಟರ್ ವಾಲಿ
or
ಆಗಿತ್ತು
in the digital form.
ಇನ್ನೊಂದು ಸೆಂಟರ್
Digital form is requires much
ಇನ್ನೊಂದು 2 to 5 minutes ಕ್ಲೋಸ್ ಆಗುತ್ತೆ.
so digital form, whatever data which are available in the computer readable format, it's much more easy to input those kind of and and edit those kind of data. So basically, while capturing the data, proper data encoding method should be selected, mainly considering three major. While capturing the data, we need to consider three major factors. So whether the data is analog or digital in its original form, whether the data is spatial or attribute, whether data is to be stored in vector or raster form. So inputting and editing of raster data. So raster data are inputted in certain ways. So scanning is the first one, first manner in which we do retrieve data from analog maps or aerial photographs or printouts of satellite image, like the hard copies, and convert analog maps into digital data in raster format. And scanning resolution is also it's a property of the scanner, which how better it could receive the data from the source. So it has some disadvantages too, the scanning, while we do scanning. So there are possibilities of unwanted optical distortions or unwanted noise. So higher resolution may create unwanted spots on the image too, whereas lower resolution, where if the scanner has a lower resolution, so it may result in loss of data. So the raster data, we can also get it from the satellite sensors and digital aerial cameras. So actually these are a computer, like these are in digital format, which is compatible to the computers or a digital database. So these can be easy to work on. And while we do editing, it's actually editing what it basically is. Before we finally using the data, we do after retrieving it, we need to put it through some process, so that it's much more, it can represent the reality in a much more better manner. So we do like rubber sheeting, we do with the raw data to bring it in alignment with the real map. Like we work on it by transforming image so that points specific in the image match corresponding points in drawing a corrected map. So if we have a corrected map and we have the data, we do rubber sheeting by if there is some distortions in the boundaries, we do it by selecting control points on the distorted map and stretching it, and where we try to overlay, or I try to bring the points in much more reference in a better reference to the actually corrected map. So second is georeferencing or registration. So graphical data in GIS should always be graphically reference it. It implies assigning geographical coordinates to the data. So we have different sets of projections or for different areas, or for coordinates to specific areas. So over here we try to, whatever image we are working on, we try to reference it to the actual to the kind of coordinates which represent the actuality of it on the ground. Like like when we because the area or it varies everywhere when we talk about the area or areas. For example, it varies at different location on the surface, so we need to put our image or data in through such projection forms, which gives which gives us the exact information. So identify the image coordinates of several point ground controlling point in raw image, match them to the true position on the ground coordinate. So we can do it in several ways, like we choose some points as ground controlling point on the map, and we go to the ground and then get the coordinates, like through GPS, for example. We get the coordinates, and we can just we can georeference it in the database management system. So third is projection and reprojection. Like we talk about projection, fundamentally is a fundamental component of map making, and is some distortion or distance direction scale is in the map projection. When we take data from an analog map, it's always a possibility, either due to distortion in the map or maybe in the projection on the map there could be some distortion. So we do reprojection by using using the computer. So we can do it in the database management system. We can actually reproject it to reconfirm or making it more better. So the fourth one is how do we do scaling and resizing. We match the scale of an image to the scale of vector drawing or another image. Scale and positioning a raster image so that it matches the scale and position of element in a vector drawing or another image. So it's basically the rescaling the image, the raw data is per our convenience or our requirements. And this speckling, removing speckles or stray pixels that can appear in the image while we scan, drawing, or blueprint the dirty or wrinkled. When we retrieve, for example, data from analog maps, so there tends to come like there would be some stray pixels coming in or whatever. So we through despeckling we could remove or eliminate, or we can correct them. So adjusting brightness and contrast. So increasing brightness reveals detail in shadow areas. Excessive can wash out the light area. So what is per our requirements, we can also work out on our raw data. We can increase the brightness if we need to work upon, like if we need to the data from the shadowed areas, or we darkens it when we have to study about the light areas. So increased contrast enhancement is distinction between dark. Increasing contrast enhances the distinction between dark and light area. Actually, the contrast, it increases the distinction between what is the dark and the light areas. And thresholding is also one process when while we distinguish between the dark and the white and the black. So segregating the image gray values into distinct values 0 to 255 separated by threshold gray values. So for example, if our data is located between the it varies from 150 to 200, so we can we can increase the variability by stretching the threshold gray, by stretching for example, the 150 to much more lower, nearer to the 0, and 255, like the white one, like the brighter value of 200, to extending it to nearer to 255. So we basically increases the contrast here too. So produces binary output and sharply defined spatial boundaries. So it defines data much more sharply. So color separation is one more data editing process, how we can edit the raster image. So each color in an image has its own channel. Like we talk about in color image, well, they are all arranged in separate layers. They have their own separate each color, each three basic color there. It has its own separate channel. So by working upon each channel, we can bring upon the color of our requirements, the kind of color which we required. So we can work upon each colors on the image individually. And subsetting actually refers to the breaking out a portion of a large image into one or more smaller image. So subsetting basically is to bring out the area of if we have a large section of data, we can bring out or we can carve out the area of our interest and reduce the image file to include only the area of interest. So it's basically to reduce the image file to include only whatever area we are interested in. And the further is edge matching. When study a span a span over several images or study area extends across two or more map sheet, we do end matching. Like we bring various images. We can bring various images together. We can put them together and combine. And while combined image create a seamless join across the two or more maps. It's for example, when our area of interest it extends or it to more than two maps. So we can, through end matching, we can just combine them in a seamless. So we can join them in a seamless and much more better manner. So these are some possible methods of data encoding for different types of data, like the tabular data, which is in analog form. We do input it, and it in a keyboard entry by text scanning or geocoding after entering it into the database. And map data, which is available in the analog form, we do manual digitizing, we do scanning, and we do raster to vector conversion after if it's required. So remotely sensed data, which if it's in an analog form, we also input it. We input it through a manual digitization or scanning or on screen, and we can also encode it, edit it in on screen raster to vector conversion after scanning. So tabular data, which is available in digital form, like digital file transfer, it can be transformed from it can be transferred from one file to another. And map data, if it's the digital, if it's in digital form, the vector data, this digital file transfer can be carried out. And in digital raster form also, we can do the file transfers and the raster to vector conversion. And remote sensor data, which is available in digital form, digital files transfer may require image processing and necessary formatting. Raster to vector conversions can also be done. So GPS data, which is available in digital form, so digital file transfer can be performed, and geocoding too. So inputting and editing of vector data. So how do we input or retrieve the vector data? So first of all is the design. It's a much more conventional process of how we retrieve data. It's one of the common way in the early days of digital cartography. Map on a digital table or digitizer. So we would have a digital table. So we would put the map on the digital table and try to retrieve each information of the map with the help of the by moving the mouse or the map. So it's much more laborious and time-taking work, and but it's a relatively older now. It's rarely been used nowadays. And process continues until desired feature are included. The process of digitizing, the process of tracing things, it is continued till whatever features which are required. And main disadvantage of how we do it in the older form is its slowness and lack of accuracy, and map shrinks or stretches when made. So it gives us inaccurate data. So vectorization and raster to vector conversion, it's much more a new form, a new way to how do we retrieve the data in a raster form. So conversion of digital raster image to digital vector data. So everything basically, when we most of the data about the real Earth, when we retrieve, we mostly retrieve it about almost all of it. We retrieve it in raster form. So we need to convert it into vector form. When we vector data are actually, they are required to be created, like while they do in the digitization, while they do it in manual form, and over here we create it by using like GIS softwares. So vectorization is much more tough as compared to rasterization, of course, and vector format requires topological structure. So simple raster to vector process is on-screen digitization. So on-screen digitization is similar to what manual digitization, but it is done on the screen, and it's much more easier and much more faster as compared to the older ones. So for example, if we convert, we can zoom the image, and we can more precisely locate the whatever, like boundaries. If we have to digitize the boundaries of a state, we can by zooming the raster image to our requirement, we can do it much more accurately and much more faster. But there are some disadvantages. Vector data generally convert to non-topological mode. Like when we digitize the vector data, it generally tends to convert in a non-topological mode. So we have to create, or later on we have to create the topological relationships. So several errors occurs in the vector. Missing link, noise of the raster are also converted into vector. Like noises of the raster images, sometimes whatever noises it have, it also tend to get converted into a vector form. So editing a vector data. So before getting it to utilization or bringing it to use, we need to do some corrections or do some editing of the data. Like we did it with the raster image, we also need to put through some process the vector data too. So we can correct the inaccurately drawn data or inaccuracies resulting from surveying, digitizing, or scanning. We can also simplify our data for plotting, making adjacent maps, and align them correctly. So first of all, like it's dissolving the pseudo nodes. Like we have nodes like is basic structure, basic representing points in the vector data. So there tends to be false node or unnecessary nodes while we do digitization. So it should be removed, because it requires to remove unnecessary nodes that are at the junction of two linear objects by leaving the vertex. Because when we do later on, when we do like topologies of the vector data, so these points, it tends to disturb, it tends to give out wrong information. So remove dangling nodes. So wherever there is a gap, or if a single node of linearity entity connect to an entity connected to an entity, other end is loose. For example, if there is losing gap between a point or a data, it would be connected. It would be so often caused by inaccurate digitizing. It often, this kind of dangling or this kind of gaps are remained often due to inaccurate digitizing or automatic conversion. So correction, the node is identified and is moved or snapped to the object to which it should have been connected. So how do we do the correction? We have to identify it and move it and snap it to wherever it should be. So removing label errors. So each polygon in a vector data, it has its own label. It has a particular label which distinguish it from the rest. So sometimes it tends to sometimes it happens that the levels of some polygon, it tends to shift. There would be missing labels, or there would be too many labels in another polygon. So these are also to be sorted out. So remove silver polygons. As we talked about what silver polygons are, like when we do double digitization, there tends to be remain gaps between triangular gaps or rectangular gaps in between. So these are actually tiny graphical polygons which has to be removed by matching vertices of alien. So by matching vertices of adjacent polygons, we can remove the silvers. So deleting duplicates. So they are, while digitizing, there tends to get created a lot of duplicates of like if a line or a point is representing, if a line is representing the same coordinates or the same distance, the same attributes, so it means that there is a duplication in which is required to be removed. And breaking crossing objects, important when we are establishing a network topology. While doing network topologies, there tend to be like when there are for example, there's a 4-liner object in a network topology, we tend to digitize at 2 lines because it's much more, it's so intensely the network, sometimes it gets they are tied out or they are very densely located. So we tend to sometimes locate, like do the 4 linear objects digitized as 2 single lines. So it is also needed to be corrected and worked out. So coordinate thinning. So generally what happens when we digitize, we tend to uses a lot of nodes while we're doing, which results in the increase of file size. So to simplify linear object or to reduce the file size and improve performance, we need to remove the whatever extra nodes or whatever unrequired nodes are there on in the vector data. So basically, this is this is a representation of the whole editing. What editing we do with the vector data. So pseudo nodes, like for example, in the middle column, we have a pseudo node while 2 points are there. We have a pseudo node which is not required. So we need to, after editing, it would be removed. So unshoot it. It's like for example, if a point, if a node remains unconnected with the attribute it is supposed to be connected with, so we can, after editing, it gets corrected and collected. So overshoot, sometimes it tend to expand or fall through the boundary, like the attributes. So it's also required to be corrected. Clustered nodes have different clustered nodes. There tends to remain danglings, and how we after editing it would be done. It would be corrected. And silver polygons for the gaps which are remained while we digitize boundaries, and after doing the editing, it would be corrected. For likewise, duplicate objects, breaking crossing objects, and coordinate thinning is there. Like previously, we had a lot of unrequired we have used a lot of nodal points. So and after editing, a lot of them would be removed to decrease the file size or to increase the work efficiency. So labeling errors, as we explained, there tend to be every polygon has its own label. So sometimes there would be missing labels, or sometimes there would be double or duplicate labels. So after correction, there would be a single label to each of the polygons. Thank you. That's all. So if you have any questions or queries, you can just ask.